lecture video for February 26th. Have your notes out. Let's go ahead and get started with a word problem. The volume of a gas varies inversely as the pressure on it. If the volume is 240 centimeters cubed under pressure of 30 kilograms per centimeter squared, what pressure has been applied to have a volume of 160 centimeters cubed? Okay, so we know that with inverse variation, it's always xy equals k. They have a constant product. But if you have a change in two variables that vary inversely, you can equate them like this, because we know that the k's will stay the same. We can just say x1, y1 equals x2, y2. All right, and now fill in what we have. So 240 times 30 equals 160 times our unknown. We don't even really have to be all that precise about where we put it in our variables because commutative property of multiplication, I just know that their products must be the same. All right, if I multiply 240 times 30, I get 7,200 equals 160y. Divide both sides by 160. Divided by 160 equals 45. So y equals 45. And then this is a pressure. We can go look at the other unit for pressure, kilograms per square centimeter. All right, and I think it should make sense that by applying a greater pressure, we were able to reduce the volume. All right, here's another quick word problem. Our class has decided to pick up trash each weekend in a local park. The table shows how many students helped each week and how quickly we picked up everything. Hopefully it makes sense that the more students come, the quicker the job gets done. We're going to assume the amount of trash in the park each week is fairly constant. We're just basically maintaining a level of cleanliness. So if only 3 students showed up, it took 85 minutes, 5 students took 51, and so on. How many students would be needed to keep the job under 30 minutes? So notice here, these two are varying inversely. One's going up while the other's going down. And if I multiply them, I will see 3 times 85, 255, 5 times 51, 255, 12 times 27, or 21, 12 times 21 equals 252. So slight change there, but if this is like real world data, we wouldn't expect it to be the exact same number every single week. And then 17 times 15 equals 255. So these numbers are close enough. 3 of them are 255 to say that this data is varying inversely. And that 255, that represents how many minutes it would take just one person. There's 255 minutes worth of work to be done, and we can divide that up by however many students we bring. All right, so we can say xy equals 255. If we want to keep the job under 30 minutes, we can plug in a 30 for one of these variables. Divide it away, so the 255 minutes worth of work divided up amongst 30 students, or 250 divided into 30-minute chunks, takes 8.5 students. We'd want to round that up to 9 students because it says we want to keep the job under 30 minutes. So 8 students would take a little bit longer than 30 minutes. 9 students, we can see 255 divided by 9 would get done in 28 minutes and 20 seconds. How quickly could we finish with 32 students? So we'll plug in a 32 on this side. Divide that 255 by 32 and we get done in 7.9 minutes. Rounding up would be 8 minutes. 7.968 minutes. So roughly 8 minutes. All right, goal for today is use our graphing calculator to discover what affects the shape of a rational function graph. Why are we doing this? We can locate the asymptotes and holes of a rational function graph. Those are the two main features we're looking for. Okay, so we saw this in class very recently, but here is a graph of y equals 1 over x. The main features are a horizontal asymptote along the line y equals 0, a vertical asymptote along the line x equals 0, and then an axis of symmetry along the line y equals x and y equals negative x. So we have two axes of symmetry, AOS, and we have two asymptotes, HA and VA. All right. So what would happen if we put a negative up top? Well, it would vertically flip this graph, and that would have the effect of making it look like these curves are not going into corners 1 and 3, but rather into 2 and 4. So we would hit the point -1, 1 and 1, -1, and then we sort of curve into these corners like this. Graph spikes up to infinity, reappears at -infinity. So we could say it fills in opposite corners. All right, the rational function f of x equals 1 over x can be transformed by using methods similar to those to transform other types of functions. A causes vertical stretch, h being added or subtracted directly to the variable moves us horizontally, and k moves us up and down. So what would the graph of y equals 1 over x minus 2 plus 3 look like? Well, this is going to be moved right 2 and up 3. The easiest way to think about this is just moving those asymptotes. The vertical one was along 0, but now it's been moved right 2. So let's add in a vertical dotted line along the line x equals 2. And similar with the horizontal, it was along the x-axis. Now it's been moved up 3. So this sort of gives us a bullseye that we are going to now try to fill the corners in. No vertical stretch or vertical flip, so it's going to hit the point that is over 1, up 1, and left 1, down 1 from that bullseye. And then we get the rest of the graph by just sort of curving this in here. Like that, and this one stays close to that line until we get close to our vertical asymptote. Then it very quickly goes up toward, or goes down towards -infinity. All right, here's another one. Now we do have a vertical stretch of 2. All right, it's also been moved left 4. Remember, this one's always backwards of what you think. When you see a plus there, it's actually left. And then this one does work how you think. This one moves us down 1. All right, so let's add in just the asymptotes to start. This one's been moved down 1. The asymptotes are not affected by any sort of vertical stretch because they were at 0, so they wouldn't be changed, and then left 4. All right, now how do we deal with this 2? So instead of there being a point over 1, up 1 from that bullseye, it's going to be over 1, up 2. But because this is symmetrical, we could also go over 2, up 1. And we're going to hit these 2 points because of that vertical stretch. We could think that this point that was at 1 was stretched up to 2. This one was at 1/2 and now stretched up to 1 above the horizontal asymptote. And now because of that other axis of symmetry, I can take these 2 points and bring them over here as well. So every time we put 1 point, we get 3 more because of those axes of symmetry. All right, and connect them up with our line that fills into these corners like that. All right, so it is possible to create a graph that's going to have 2 vertical asymptotes and also have a horizontal asymptote. So what's going to happen there? So let's put in a horizontal asymptote and 2 vertical asymptotes. Let's do this twice because there's 2 different ways that this can happen. So remember, our graph wants to stay close to that horizontal asymptote for the majority of its life. For most numbers, it's really just close to this line. But then these walls get in the way, and it has to go either up and over or down and under them. And every time you go down to up to positive infinity, you're going to reappear at negative infinity. If you ever go down to negative infinity, you'll reappear at positive infinity. So our graphs can loop in 2 different ways. They can go down. If it goes down, it's going to reappear at positive infinity. Or they could go up, but the important feature here is in the middle section, they can either turn and go back up and then reappear. So you can have a graph like this or this vertically flipped, or in that middle section, you can make kind of an S turn and then go the other way past the next wall. So this one, we could go down under this, which would cause us to reappear at positive infinity, but then make like an S turn, go under this one as well, reappear at positive infinity, and then get back to staying close to that horizontal asymptote. So you can either make a U-shaped, or you can make an S-shaped. And this is true if we have even more vertical asymptotes. If we have 3 or 4, in those intervals, we can either turn or kind of zigzag, but keep going. All right, what does a hole in a graph look like? So this is where we're going to need those graphing calculators. Let's graph this function in our graphing calculators. As you plug it in, you're going to need to use a set of parentheses to keep the numerator separate from the denominator. So you go y equals x squared plus 5x plus 6 on the top. So parentheses x squared plus 5x plus 6 divided by x squared plus 6x plus 8. Oh, forgot my parentheses. Need that parentheses there, or do the wrong order of operations. All right, let's just do a standard viewing window, so zoom 6. Okay, so we see it does have a vertical asymptote here, and it seems to be following a horizontal asymptote as well. Let's go back to this problem. We know when simplifying rational functions, factoring is a really important skill. So let's go ahead and just factor this, just because we think it might be important. So I need on the top 2 numbers that multiply to be 6 but add to be 5. That's going to be 3 and 2. And on the bottom, 2 numbers that multiply to be 8 but add to be 6. That's going to be 4 and 2. Okay, so I know that because I can't divide by 0, x cannot be -4 and x cannot be -2. Those are the 2 values that would make this equal to 0. Well, let's see what's happening at those 2 values. So at -4, that's right where we're finding this vertical asymptote. What's happening at -2? It doesn't really seem like there's any feature there. So let's go to the table. I'll have it start at -5 and count up by ones. And I go back second table. Okay, see at -4, error for the vertical asymptote. But at -2, there's an error as well. Even though it looks continuous, there is a little gap there where we can't evaluate our function. If we want to like really zoom in on that gap, we could change our window to go from maybe -2.01 to -1.99. Let's see if it actually shows us a gap if we zoom in that much. And yes, it does. You can actually see a small break in the blue line right there because at exactly that value, we cannot evaluate our function. All right, so what does the hole in the graph look like? Your graph is just going along. Can have other features, but it's just sort of going along, and it just skips a value, but then it stays continuous like this. Now, can we tell why -4 was the vertical asymptote, but -2 was the hole? Well, that's because -2 is the factor that cancels. So if the factor cancels, it'll result in a hole in the graph. If it doesn't cancel, it results in a vertical asymptote. All right, I'll bet a few more questions here, but that's that for this lecture video. Have a good rest of your day.